Hello, my friends of Hatari Labs. My name is Montoya. Please welcome to this tutorial. This tutorial is the most simple seawater intrusion tutorial made with Modflow6 and mf6Voronoi. Okay, what we are going to model. Why is simple? Because in this tutorial we are going to be focused on the the process itself and how things work on a seawater intrusion model. Okay, what do we have? Here we have some wells, we have the model limit, we have the sea, we have an area for refinement, and we have a general head condition here as well. Okay, and we have a cross-section line. Just to mention that this cross-section line is in the mean that is not on the entire model but is just on this part. Okay, and as well we have some observation points. Okay, so let's see and let's work with the model. No, cancel. Okay, what you are going to get on the folder is you are not going to get this here, this tree. Okay, I'm going to close the as well. Okay, you are going to have the executable, the raster, the scripts, and the shape files. Okay, so everybody please start Anaconda prompt. See the documents, see the simple. Okay, and here we launch Jupyter Lab. Okay, the first thing that you have to do here is to, here on scripts, you have to create a new notebook that is going to be called part 0. And here you are going to pip install score mf6Voronoi because you need the latest version of mf6Voronoi. Okay, that is at the time of this tutorial is 0.0037. 0.0037. Okay, so we comment this, please. Okay, first of all, what you have to do, there is a new template, okay, for this, which is this new template. It's a template because this is the most simple tutorial for seawater intrusion. Okay, because there is a template for seawater intrusion. Okay, so first we are going to generate the mesh intrusion. Okay, then we are going to copy the template for intrusion. Okay. Okay, and then we are going to copy the VTK generation for intrusion. Okay, great. So let's go for the mesh generator. Great. So here we are going to use, okay, because this is simple as well, we haven't worked into going to the minimum size. Okay, so we are going to work with refinement that go from 250 to 50. Okay, that is enough to represent the overall response to seawater intrusion. But however, you can play around with finer discretization. Okay, so there is a model limit. The wells are also in the grid. The refinement is also on the grid. The sea is also on the grid, and the regional is also on the grid. The regional flow. Great. So there is a okay. So we have to run the first. okay, and then the second, and then we generate the vertex. This is a very lightweight model. It only has 3,000 points. Okay, and then we store the okay, great. So here we are going to show the mesh. Pretty simple. The sea, the refinement, the wells, the general head, and there are some wells here inside. Okay, and from the wells we are going to okay, so we generated a JSON with the mesh dict. Okay, then we go to the seawater in okay, the to the seawater intrusion. Okay, so on the seawater intrusion we run the first cell, we open the dig, we have the geometry, we open the them. Okay, and some dams, I mean, are not, I mean, have some elevations inside the where it is supposed to be sea. So we have done this arrangement in order to see that for every cell that is in that that is interpolated from the dam, okay, but is inside the sea, the elevation is 0. Okay, this is a fix to the elevation, but it's very practical when we work with the in order to prevent incorrect geometries, or like the head of the cell is below the cell of the bottom. Okay, so we 8 meters minus 30 is the bottom of the is you can play around with minus 50 as well. We are going to work with 8 layers, sorry. Okay, so we create model files. The model works with 50 years on the steady state and 30 years on transient. Okay, this is the flow model. The solver for the flow model. This is the discretization. We can plot the discretization. Okay, and then as well on a cross section. Okay, we have the initial conditions, and then the K. We have the K for the first 3 layers, the second 3 layers, and the last 2 layers. And the first 5 layers are convertible while the bottom are confined. Okay, the storage, we only have 2 boundary condition, 2 steady state, 2 stress periods, sorry, recharge and evapotranspiration. We define the intersection object, okay, and for the for where there is this regional head boundary, okay, it will apply the elevation, and it will be located at the cell of the water table corresponding to the water table, okay, and where is C, okay, it will have elevation of 0, okay, and a conductance of 0.2. Okay, this is, you see a number here, this is a auxiliary, and you need that auxiliary because this auxiliary will link, okay, the flow to the transport, okay, because when you do seawater intrusion, you do a variable density flow where the head is actually corrected by the density distribution. Okay, so here we have we initialize the GHB, and then here we define the buy package for the flow model over the concentration, where for the normal with the 0 concentration the density is 1000, okay, grams per liter, or liters no, kilograms per cubic meter. Okay, but when you have a concentration of 35 grams per liter, the density is 1035 kilograms per cubic meter. Okay, so this creates a slope, and then you define it here. You can define many species here as well. Okay, so we have the GHB at the layer 0. Okay, great. So this is the sea and the regional flow. Okay, and then we apply the wells. The wells are located at a depth of -20. Yeah, and they will be pumping just 0.05 liters per second. Okay, then we have the obsdict. Then we are going to get the water balance for the well. So this is well location on layer 6. Then we have the transport model. Okay, then we register. We have a okay, then we have the starting concentration for the okay, and on the cells that are located in the sea, okay, will be applied as 35 as the initial concentration. So we have here the initial concentration, okay, um, and but the initial concentration is for all layers, okay, that is why here you see. Okay, you put the advection, dispersion, porosity, and source on record rate, okay, that is linked to the concentration. However, I have assigned it not as a single source, but as a constant concentration. Okay, so this will be applied as here, and on observation points, here you see these are for the observation points that will be implemented on the model. Okay, we have the output control and the exchange in between the flow and the transport. Okay, we write the simulation. Okay, and there is a trick here. What is the trick? The trick here is that here on mf6 num, you have to define first the flow model and then the transport model. Okay, and otherwise it won't run. Okay, now it's running. So we can see the heads of the first stress period. Okay, so these are the heads of the first stress period. And then with pumping will be this one. Okay, this is with pumping as well. This is on the cross section. And now we can work with the constant concentration. Okay, with the concentration. This is the seawater intrusion. Okay, because sea actually is here. Okay, and this is how the seawater has inserted. Okay, if you want to compare with the original one, and this is at the end of the first steady state. Okay, so that will be the okay. Then we have to do the VTK. The VTK. Okay, so we start this one. We open the model files. We initialize the VTK folder. We list the models. there are two models. We are going to work with the flow model. Then we get the observation for the period 1, and then the head for period 2, and the head. Okay, great. So that is amazing. Okay, give me 1 second. Okay, and now we are going to do some improvising because actually the code. So we are going to get the code. Okay, first we are going to get the transport code that is called model by, and then we get the times of the transport. Okay, these are the ones. Okay, so we get the concentrations for the time for the end. Okay, and then here we do the concentration of year. So we have done year, which year it is, year 30 plus 80. Okay, so this will be 80, and this is in stress period so we have period 1, stress period 0. Okay, great. So now we have the VT case. Okay, so we can open this with ParaView. So we go to the simple, we go to the BTK, and here we have the concentrations. Okay, and then here you can see the concentration, but you can apply a threshold here because the concentration actually are not negative. So you can go from 1 to 35, and then you can see the clear extension of the concentrations. Okay, so that is amazing. This is done with Modflow6 and mf6Voronoi. I hope that you find this useful, and then you can apply. My recommendation is that you follow this tutorial and then you apply this to your own cases. Okay, just to mention that we are a blog dedicated to knowledge sharing in groundwater resources. So we are hatarilabs.com. And then we have a coming course in Modflow6 in mining. Okay, so if in case you are interested. Okay, and then if you want to keep supporting our research, you can be one of our Patreon, because we have 16 Patreons, active Patreons in Patreon. Okay, so it's patreon.com/hatarilabs. Okay, thank you for following us. Hope to see you in coming courses, webinars, and so on.